Morning, this is Mark Oswald from Overland Conveyor Company. Today I'd like to go over the new changes to the power calculation methods that CEMA has just recently published. In April of 2014, the Conveyor Equipment Manufacturers Association of North America, CEMA, published the 7th edition of their book, Belt Conveyors for Bulk Materials. In that, Chapter 6, the new power calculation methods have been implemented. Some changes have been made, and we've implemented those changes into Belt Analyst version 14. The next few minutes I'd like to go over what those changes are, how they've been affected, and how you can use them effectively. First off, let's summarize what happened in the 7th edition of CEMA. First of all, the standard calculation method, which Belt Analyst refers to as the 5th edition of CEMA, has been taken out of the book and included as an appendix as a historical reference. We are going to leave the 5th edition calculation methods in Belt Analyst because a lot of people still use them. The universal calculation method has changed rather substantially. In Belt Analyst, we're going to leave the old 6th edition methods, but we're labeling them as obsolete because the 7th edition book does overwrite them. So we do recommend that you use the 7th edition universal method whenever possible. There are 6 things noted in the book that have changed. First of all the equations are now noted in imperial as well as metric units. We won't talk about that. The second one, the temperature correction factor for idler seal drag, is a relatively big change. We'll talk about that in a minute. The rubber cover indentation losses is another relatively big change. We'll talk about that in detail. And the way the idler misalignment terminology and defaults are included are a little different, so we'll talk about that as well. The sag trampling loss methods and the last two there we really won't be talking about in any detail. They're relatively minor. This is a recap of all the resistance methods. It was first published in CEMA 6th edition as a universal method. Energy losses, lifting and lowering the load. At the bottom there, point resistances for pulleys and belt cleaners and plows, etc. The main resistances are what we're going to talk about today, 3 of these, but first of all we're going to talk about the viscoelastic indentation of the belt, or the rubber rolling resistance. The rubber rolling resistance is based on several factors. The top chart here, the normal force, how the load is actually pressing on the rubber, is obviously a very important factor. Secondly, the rolls itself, the material, the steel sleeves of the rolls, or rubber, whatever they are, the diameter of the rolls, and the RPM, or frequency of the rolls, or how fast the belt's moving, is a factor. The rubber properties themselves, the viscoelastic properties of the rubber, is very important. The thickness of the rubber, and then the temperature, the ambient temperature. Those are all factors that goes into rubber rolling resistance, and it makes it a very complicated process. It's not just a matter of using one number to vary all these properties. They all vary in a non-linear manner, and that's what we're here to talk about here for a few minutes. In CEMA 6, all those items were identified, and all of them could be changed except for the actual viscoelastic properties of the rubber. There still wasn't an accepted method everyone could use to come up with these methods, so the CEMA book just defaulted to a default rubber and didn't give you the option to change that. That's changed in the 7th edition. There now are 2 methods for changing this rubber. 2 methods because, again, not everyone is agreed on what that best method is. Hopefully the 2 methods do match up fairly well, but there are differences in how these are generated and how they're used, so we're really going to talk about both of them for a little bit here, and we're going to talk about what the differences are, how to use them, and how to use them particularly in Belt Analyst. I'm going to talk first about what we call the small scale sample method. It's called small scale because the actual samples of rubber that we use are small, 3 millimeters by 12 millimeters by 30 millimeters, so about 1/8 of an inch thick by 1/2 inch wide by 1 inch long. Pretty easy to get that sample, and you can even go to a used belt or an old belt in the field and get a lab to prepare a sample from it. Take that small sample, we put it in a test machine, in this case RSA dynamic mechanical analyzer, which was a desktop type machine, relatively inexpensive to get. And we test it. We test it through a full range of frequencies. We test it through a full range of temperatures, and we also can test it at different strain levels. All three of those are important criteria in our conveyor analysis: different frequencies, different tensions, and different strains. That RSA test machine generates a whole bunch of raw data, as shown here in the lower right of the screen. This data is then just mathematically manipulated through a series of industry accepted or academic accepted calculation methods to manipulate that data into what we refer to as a rubber master curve. This master curve is very important. It shows us in this case, the G prime, G double prime moduluses through a full range of frequencies. Think of the blue line as the forces required to indent into our rubber, and the green line being the rebound. The rubber is the forces are removed, and the differences between those two lines could be considered the losses, the loss in power as we indent into the rubber. We can now put this master curve data through a series of strains, and which gives us a series of calculations, equations, which then can be added to our belt conveyor, our belt analyst predictive power calculation tool. So once we do this test one time on a particular rubber, we can then apply these properties to just about any conveyor, or really any conveyor application that we want to apply it to. CEMA has provided us 4 categories in the new book of rubbers that we can use in our predictive calculation methods. These are shown here in figure 6.49 from page 166 in the book. And a couple of things you'll see here. First of all, the default rubber, the solid line, hopefully matches up with some of the old calculation methods in the CEMA 6 book. But we have 3 new categories. We have T3, T2, and T1, as the book calls them. And you can see there that the lines vary. In other words, the relative indentation resistance varies quite a bit, and we can show it here in reference to our temperature range of plus to minus 20 degrees C. You should note here, in particular, T3 has a top in it. In other words, it is not linear. And you can see there that the worst case indentation is not at the worst case power, and this actually occurs for all 4 of these. It's just a matter if we spread that temperature range out far enough, we'd see that there'd be a hump in each one of them at various temperature levels. Now, this is a very important criteria as we move forward, that this rubber indentation is not linear. It's a non-linear property with temperature. Now, as we move forward and we talk about Belt Analyst, there's actually 3 of these data that we've included in Belt Analyst version 14 as our rubber categories. The default, obviously, and then we've included what we call good, which is the T2 category, and then we've included one we call LRR, as low rolling resistance rubber, and which is the best of the 3 categories. We have left out T3 in this case, as it doesn't really follow any of these particular criteria of default, good, or LLR. And we'll come back and talk about these 3 categories a little later and how we use them in our future Belt Analyst program. Now we're going to talk for a minute about the large-scale sample test method. By its definition, large-scale test method really talks about the fact that the test sample itself is much larger, 350 millimeters by 4.8 meters long, or 1 foot by 16 foot. And it's a full width, full gauge of belt. It includes the carcass, top cover, bottom cover, so it's much more difficult to get samples made, samples for this particular test machine. You can see in this video here, we're really seeing an example of what this test machine is testing. A full belt width, or not full, but 1 foot wide, belts going around two pulleys at whatever speed we want it to. The top roller exerts a pressure on the belt, simulates what the load is on the belt, and we measure the resistance on a load cell there, represent F sub E. So we can take this machine now, we can put an actual belt on it with a particular carcass and a particular cover gauge. We can put a particular load on it, run it at a particular speed, and we can adjust the temperature. We can heat it up, we can cool it down, and we can do recordings of what the resistance is in the rubber. And of course, if you want a temperature control, you need to have an enclosure to temperature control it. This little video is a representation of the machine that's at the University of Hanover in Hanover, Germany, and it measures the belt properties per the DIN specification for rubber indentation resistance. There are a lot of people that like this large scale sample testing because you're actually measuring actual measurements from an actual belt sample with a known load, and you can measure actual values. So it does probably is a much more acceptable method by a lot of people. However, it is very hard to use this method as a predictive tool in software because you have to do lots and lots of testing. You have to have lots of different belt constructions, lots of different carcasses, lots of different cover gauges, and run it at lots of loads and speeds and different temperatures to get a full range of values. And if you're not a belt manufacturer per se, this could be a very, very expensive process because you need access to an awful lot of belt samples and awful lot of test samples. This is the reason that Orland Conveyor for belt analysts has chosen to use the small sample scale method as the predictive tool in the program. It's relatively easy and cheap to get samples of rubber. Once you generate the master curve for that rubber, you can use that for any application, which includes any belt construction, any belt speed, any roll diameters or configuration of rolls, troughing arrangement, different roll diameters on different rolls in a troughing idler, different loading, and of course different temperature ranges. So OCC recommends using this small scale method for predicting, and then let the manufacturers use the large scale sample as verification. In other words, once you calculate the indentation drag for a particular conveyor in a particular application, then you can get the belt manufacturer to verify that the actual indentation in the large scale sample testing does match up, and hopefully it will in most applications, or at least get pretty close. So how do we use this knowledge in Belt Analyst? Well, first of all, Belt Analyst now includes a drop-down list to represent the top cover rubber type and the bottom cover rubber type, and there's 3 options in each one: default, good, and LLR. If you're using turnovers on your belt, then you only have bottom cover options because the bottom cover would be in contact with the idlers in both applications. Of those 3 types, you'll see here that some recommendations is what we suggest to use, and then what do you do if you use one versus the other versus selecting a particular belt manufacturer. First of all, if you don't know what to do, use the default value. If all else fails, use the default value. That'll give you the most conservative answer, and the default value should cover all belt options you'll come across. And if you're using a fire-resistant belt, please use the defaults, because fire-resistant or flame-resistant belts do not normally have good indentation properties. If you're going to select a natural rubber belt, such as a DIN X or an RMA grade 1, you can use the good properties, because those are typically good property belts, good rolling resistance belts. Also, if you're using just a typical high abrasion resistance rubber from a major manufacturer, you can probably use the good category. If you're using a belt that's specially compounded by a major manufacturer for low rolling resistance, you can probably use the LLR category. But if you use the LLR category, you should be aware that you need to send the belt analyst printout to your belt manufacturer and let them confirm or verify that the compound that you've selected or they've recommended to you does meet the rubber indentation as calculated in belt analyst. You can see here in belt analyst, in the carry and the return side of the conveyor, there is a printout that shows you what the drag is in newtons per millimeter for, in this case, the carry side idlers and the return idlers. And you need to give these properties or these calculations to your manufacturers for the various loads and the various temperatures that you're going to be using, or at least the worst case conditions, and let them verify for you that those are accurate, or let them give you the values that you should use in your calculations. You can always go back to belt analyst and use the multipliers to increase or decrease the actual belt deformation for your example. You might be asking yourself, is this all worth the effort? Well, in CEMA7, one of the belt manufacturers actually published an actual case study where they had a long flat conveyor, and they had a RMA grade 1 rubber on it, and measured the actual power requirements on that conveyor as fully loaded, 2,200 tons per hour. Then they replaced the belt with a low rolling resistance rubber, measured it again, and you can see here in this plot that's published in the book, where you can see the differences based on tonnage and on the x-axis of the power requirements for the grade 1 rubber versus the low rolling resistance rubber. And as you can see here at 2,200 tons per hour, the actual calculated collected data, actually not calculated but collected data, showed a 20% less power required for the low rolling resistance rubber. So yes, it can be a very significant number, and certainly worth the effort to do the analysis. But you can use belt analyst to help you decide whether this is worthwhile or not. For instance, not all applications it is worthwhile. If you're in inclined belt, high lift belt, where most of your power is in lift, changing the rubber indentation properties may have very little effect on the overall power requirements. Whereas a very flat belt, a long distance flat belt, it may have a very significant influence on the total power. Let belt analyst show you. You can go to the power calculations and look at the pie chart and see exactly what percentage of the power is in rubber resistance, and you can also switch back and forth with different rubbers and see exactly what effect that has on the overall system design. The next item we want to talk about, category here, is idler seal friction, and particularly the effects of temperature on the idler drag. Here you can see that temperature is definitely, idler seal friction is definitely affected by temperature, and the temperature effects are improved or enhanced in the CEMA7 methodology, and you will see large changes in the new calculations versus the old ones in some cases. What you're looking at here is figure 6.27 on page 154 of the new book. The solid line here labeled CEMA historical is the temperature correction factor, and that you used to see in all versions of CEMA, 1 up to 6. And you'll see here that there is no real temperature correction factor. The factor is 1 from freezing, 0 degrees C, all the way up to 120 degrees or 50 degrees C. And then it starts exponentially getting higher as you go into low temperatures. The new formula, which is the dotted line or dashed line there, shows that the temperature correction is not ever 1, but it goes through a sort of a curved line here all the way from low temperature to high temperature. A couple of things to point out: at minus 40 degrees C, the temperature correction of 3, it really hasn't changed from the old method. But as you get warmer, you'll see the temperature correction goes below 1, and also probably most importantly at freezing, where we used to be have no temperature correction factor, the temperature correction is now approximately 1.5. So what you'll need to be aware of here is that if you bring up old files that you've used in Belt Analyst before and use the CEMA7 calculation method, you are going to see differences in power just simply due to this temperature correction factor. Another thing that we want to reiterate again is that there are lots of variations in idler seal friction between manufacturers, between suppliers. So please don't believe that everyone has the same number. And for design purposes, we have to keep that in mind, especially before we've selected a particular manufacturer when we can get real values. These changes are due to different seal types between manufacturers. They're due to different greases that might be used, and also the way temperature affects each idler. This plot at the left that's in the book now, it shows drag versus RPM for 5 different manufacturers. And you see the huge range. At 500 RPMs, you see the range goes from about 3.5 inch-pounds all the way up to 8 from between these 5 manufacturers. And if we go to the graph over here on the right, you'll see again each manufacturer there is quite a range in the effects of temperature, mostly directly related to the drag at one temperature, and therefore the high drag in one case gets more greatly affected by temperature and that same manufacturer. So it's important to remember there are differences. It's also important, however, to remember that the low number is not necessarily the best number. The low values typically relate to less, as far as seals are concerned, less contact seals, for instance. So higher quality seal usually means higher drag. If you don't require a very high quality seal in your application, for instance an overland conveyor where it's not subjected to dusty conditions, you might opt for a lower drag idler. But in a lot of cases you might want the higher drag idler with the better seal. So the numbers don't mean high or low, doesn't necessarily mean good or bad. It just means there are differences, and we want to keep that in mind, and that in the end when you're doing your calculations, you want to, once you've selected an idler manufacturer, you want to get those real values from them, put them into your calculations, and make sure that you're using accurate values for your calculations. The next slight change that we want to discuss is the way the idler installation tolerances is now input. It used to be in version 6, it showed up for the first time. It is a very important part of the calculation. We encourage you to pay attention to this, but it used to be you could just only input a value, an actual value, and most people didn't really know what value to put in, and there was no suggestions on how to change that value. So in the version 7, the values can now be put in as an angle, an installation tolerance angle, how well the idler is aligned to the belt. And it should provide a little bit more accuracy in how you are able to put in that value and how to change it depending on the installation tolerances or requirements on the conveyor. For instance, if your idlers are installed on a permanent rigid structure with deliberate alignment procedures, it's now recommended or suggested by CEMA that you can use a 1/4 of a degree misalignment. If idlers are installed on structural steel without any alignment procedures, perhaps a 1/2 degree. If idlers are installed on independent imprecise footings, perhaps 3/4 of a degree. And it suggests that idlers installed in difficult mounting conditions such as unstable footings or underground conveyors, that you might use 1.5 degrees. We will suggest overland conveyor from our analysis of actual field installations that the 1/4 degree is achievable, but the 1.5 degrees for underground installations, probably the maximum there is about 1 degree of misalignment. So put in those values, and you can actually, the program will adjust based on belt width, and probably give you a little bit more accuracy as far as how that is input into the program. As far as putting in the program, you'll see now we have 2 options for installation tolerance: the actual value in this case 0.55 inches, or the angle, in this case half a degree. And if you put one in, it'll calculate the other for you. Now, the most important thing we can tell you about the new CEMA7 universal power method is that because of the non-linear nature of the rubber indentation, that the highest power calculation may not be at the lowest temperature. As you'll see here in this plot, we have a temperature sweep between -30 and +30 C, and you can see here that the power actually goes up until we get to about -18, and then it starts going back down. And that's because most rubber indentation has a hump, and it will start going back down at the extreme low temperatures. So this is very important. We can't just look at the highest temperature and the lowest temperature anymore. We have to have a way to look at a sweep and actually find the worst case temperatures for our calculations. So to help you with this, we've included a new feature in Belt Analyst version 14, which we call the Power Wizard. And the Power Wizard button is right up by the temperature inputs on the main screen. And when you punch that, you get a new screen that looks like this, which gives you the ability to put in a temperature range from the highest to the lowest, and will automatically plot a complete set of calculations between the high and low temperatures. But in addition to that, it allows you to put in tolerances for our three most variable drag parameters, and that is our idler drag, our installation tolerance, and our belt cover or rubber cover indentation. So we can put in a plus tolerance to get our high power condition, we can put in a low tolerance to get our low power condition, and along with the temperatures plots sweep, we can see you can get a plot of our complete power possibilities for the particular location condition that we're looking for. And the program automatically pulls off the high value, shows you what that is and what temperature that's at, and it also shows you the lowest power values and what temperature that's at. So this Power Wizard is very powerful. We highly recommend that you use this Power Wizard often, and particularly when you're looking at low temperature conditions, to make sure that you're finding the proper high and low power condition, as well as look at all the variation possibilities in your power calculation.